Okay, it looks like it's 11, so we'll go ahead and get started. Get back to this camera. Okay, just in case. All right, so let's take a look at the slides for chapter 21. This is the slides with the clicker questions interlaced. And then I also have the slides that I make as lecture notes that just have like the book's highlights or whatever. So just in case we need that, 'cause sometimes I find the slides that the book what do they call them? Publishers. Sometimes they're lacking, right? So, but we'll take a look through the chapter 21 stuff. Hopefully you got comfortable with the Z procedures and the T procedures that we sort of built on the back of the Z procedures. In the T procedure so far, we've been taking a sample from one population and trying to compare it to a previous mean, for example, of that population, because, and or we've been, if the mean wasn't known at all, then we were trying to like make an estimate for that mean using the confidence interval, for example. And that was all one sample for one population, right? Now what we can do, or what we're going to be able to do here is two sample T procedures so that we can take samples from two different populations and then compare the means of those populations. So for example, if we took some information about dogs, right, and some information about cats, those are two different populations, but we could compare the results, right, and discuss if one gets heartworm more than the other or something like that, right, kind of thing. So this time around, we are stepping up a notch because, again, we are going to have two samples from two populations that we're comparing, which is going to complicate the formulas a little, but they're still just building on the old formulas. So it went Z-score from chapter 3 to Z-score from chapter 15 to then the T-scores from chapter 20, right? And now step it up a notch, right? So in chapter 21, we're going to compare two means. Let's see, where do I click? In chapter 21, we cover two sample problems, which will be comparing two population means, which is going to be giving us the two sample T procedures. They have technology for this, right? Like in your TI-84, robustness. And then we won't look at the next set of starred topics, details of the T approximation. They are sections in your book. Avoid the pooled two sample T procedures. So just note to self, if you are using the calculator, the TI-84, then you'll see a question like pooled question mark, and the answer is no. Like you do not want to pool the two samples together. So that's a warning. And then also avoid inference about standard deviations. So we've been doing inferences about means, right? And we can do them about proportions, which is chapter 22. I keep thinking we were already to 22, but proportions is chapter 22 when we come back from break. And the other thing we can make inferences about is standard deviations, for example, because right now we're like, we don't know the standard deviation, and we're just going to pretend it's the standard deviation from our sample, right? And so, yeah, at some point, there are chapters and procedures to make this kind of inference, but they're telling us to avoid it. So we don't even do it as like undergrads, right? And then we've got this permutation test as well. So all the starred sections of your book are optional, and we opt out. Right? Otherwise, if the subjects do come up, then just you can email me, let me know. I can help explain it, or the sections are there in the book. I always recommend the stats tutors in the Launchpad as well, because they're very animated, which is something I appreciate. Like, I'm a visual person. I like to have a visual example provided, right? And the fact that those visuals are in color and you can manipulate them, or they do that for you, that's appreciated, right? So if that appeals to you as well, then look at those stat tutors, right? So for example, when we first got sent home for COVID, that became the lectures, right? Like, those stat tutors became the lectures for students back in the spring of 2020. So don't hesitate to use every resource to your advantage. So let's look at the two sample problems. A two sample problem can arise from a randomized comparative experiment that randomly divides subjects into two groups and exposes each group to a different treatment. Comparing random samples separately selected from two populations is also a two sample problem. Unlike the matched pairs design studied earlier, there is no matching of the individuals in the two samples. So like with cats and dogs, we're not matching one cat for one dog, right? Like, there's no pairing up going on at all. We're just like looking at the information for cats and looking at the information for dogs, and then we're going to compare that by standardizing those scales and whatnot, right? So we have these two different types of two sample problems, right? The two samples are assumed to be independent and can be of different sizes. So like, you have 100 dogs and you only have 75 cats, right? But that's okay. The most common goal of inference is to compare the average or typical responses in the two populations. And now this screen, when it's got that green banner at the top, this is us flipping over to the clicker questions, right? So these are more like the beginning questions in the book, as well as your like learning curve questions, where you're building up your understanding, right? So right now we're just going to decide if these few examples are matched pairs or if they're two independent samples. So like cats and dogs, right? So to study the change in attitude towards statistics over the course of the semester, a professor selected a simple random sample of students. She administered a questionnaire to the students at the beginning and at the end. Oh, sorry, I got excited. And again at the end of the semester. What type of problem is this? This is a matched pairs design. You are the pair, right? So like, you are the same individual in both samples. The samples are about the same population, right? You're an individual in both of those samples and in both of those populations. And so you're asked something at the beginning of the class, and then you are asked something at the end of the class. So you're participating in both. So you're forming a pair, right? So that's a matched pairs design. The National Park Service compared the average amount of money spent by visitors into two different national parks. They sampled visitors on the same day in each of the two parks. What type of problem is this? There's no one-for-one pairing, right? And the individuals are from two separate parks altogether, right? So like, if we're talking about the Grand Canyon, that's tens of thousands of people, right? And then if you're going to compare it to like something we have around here, you're talking only maybe thousands of visitors, or maybe we have tens of thousands of visitors and they have 100,000 visitors, right? Sort of thing. So these are two wildly different populations of people, right? And so we're also having two independent samples, right? And like I said, we might not even have the same number of people that get asked or anything. Okay, so researchers at a pharmaceutical company tested a new sunscreen formula. They applied the formula to one arm and the old formula to the other arm. So the new one goes on one arm, the old one goes on the other arm. You again are the individual in both samples, right? You're an individual in the sample for the new formula, and you're an individual in the sample for the old formula, right? And so randomly choosing the arms for each formula. So, like if you drive in America, your arm is getting toasted on the left side all the time, maybe, right? Because that's the one exposed to the window. And so they want to randomize the formulas that get put on the sun-crested arm versus the other arm, right? And so definitely they want to randomize what ointment goes on which arm, right? But again, this is a matched pair. You are an individual in both samples, right? You're literally putting the two creams on yourself, two different arms, right? So same individuals in each sample, same population, right? So it's not two independent samples, it's a matched pairs. A dairy scientist compared milk production of cows fed two diets. So these cows are fed two different diets. He randomly divided a set of 10 cows into two groups. One group was fed diet 1 for a month, and the other was fed diet 2 for a month. What type of problem is this? So here we have two independent samples. One thing that stood out to me was that we weren't necessarily told that these groups were split evenly into like 5 and 5, like that was something that stood out to me. But also what stands out to me is the individuals are completely different, right? And they're not getting paired up for comparison reasons. They're not like saying, okay, we've got we made sure, well, they're all cows, so technically they're all females, right? If we're going by the definition of cow. And then, so one, we know they're all females, but maybe they would pair them up to make sure there was a young one and a young one, right? Or a tall one and a tall one, or a heifer and a heifer, right? That sort of thing. But they're not pairing it up in any way. They're just saying, they're rolling a dice, right? And they're saying, if I roll an even, you go to this group. If I roll an odd, you go to that one. And for all we know, one group has like 3 members in it and the other group has 7, right? We don't really know. And so this is 2 independent samples. Yeah, so that one's a little weird, but this will be the other thing, right? So a dairy scientist compared milk production of cows fed 2 diets. He randomly assigned 10 cows to be fed one diet for a month and then the other diet for a month. The order of the diets was determined randomly for each cow. Milk production during each of the 2 periods was recorded. So now I'm a cow, right? And I'm eating like alfalfa for a month, and then I go and I eat hay for a month, right? Or whatever they feed cows. And then I'm a individual in both of these samples, right? And so my results for eating alfalfa are compared to my results for eating hay, right? So this is a matched pairs design because of the reasons I stated, right? Generally, we didn't see any kind of pairing up like husband and wife or twins or parents and children, right? We didn't see any of that kind of stuff. We saw in all of these that the individual took on 2 treatments, right? These cows took on 2 diets. The arms took on 2 different sunscreens or whatever we were looking at, right? And then there was another one, but I don't remember it. Okay, so the blue swirly top means we're back to the slides, right? So those are the different types of slides, and I kind of like to lace them together versus looking at one whole set and then the other whole set, right? So I don't know. I also like to try to use all of your resources to your advantage so that you know what's out there for you. Okay, so comparing two population means. Conditions for inference about comparing two means. We have two SRSs, so two simple random samples from two distinct populations. So two different groups, right? The samples are independent. That is, one sample has no influence on the other. We measure the same response variable for both samples. And another condition is that both populations are normally distributed. The means and standard deviations of the populations are unknown. In practice, it is enough that the distributions have similar shapes and that the data have no strong outliers. So this is like a realistic situation. We don't know what the means of the populations are, and we don't know what the standard deviations of the populations are, right? All we're going to know is what the mean and standard deviation is for the samples that we select, right? That's it. Okay, so call the variable x sub 1 in the first population and x sub 2 in the second population in the second, because the variable may have different distributions in the two populations. So these are probably x bars that we're looking at, but I'm not sure. They don't have x bars, so we'll just call it x sub 1 and x sub 2. And I'll probably even just call x1 and x2 as something. So here is how we describe the two populations. So we have here a contingency table. We have in the rows population 1 and population 2, right? And in the columns, we've got population 1 and 2 variables, x sub 1, x sub 2, describing means mu1 and mu2 with standard deviation sigma 1 and sigma 2, right? So this is how we describe the two populations. So we don't know any of this, right? Like our variables, what we're looking at, but we're going to end up with a sample that gives us a sample mean, right? So at some point we will have an x bar sub 1, but not right now. Okay, so comparing two population means, here's how we describe the two samples. So here's our x bar, right? It's a little tiny bar in these slides, but there it is. So here's our sample. So from population 1, we have a sample size for the first sample of n sub 1, a sample mean of x bar sub 1, and a sample deviation of s sub 1. And for population 2, right, cats and dogs. So for population 2, we have a sample size labeled n sub 2, a sample mean labeled x bar sub 2, and a sample standard deviation labeled s sub 2, right? And so we just put these little subscripts in there so that we can differentiate between the two different n's that we have to identify, right? And the two different means that we have to identify and the two different standard deviations that we have to identify. And so if you call your first group population 1, you have little ones as subscripts. If you call your first population cats, then the book would write cats, right? N sub cats, x bar sub cats, s sub cats, for example, right? So I agree it can be a little confusing because sometimes they use inequalities in the subscript and then inequalities in the hypothesis test, and those can be hard to look at. So try to, if you want, just rename your population 1, right, versus population 2 and put in these subscripts. It could help clean things up a little for you. So just the notation gets a little hefty, right? So to do oh, sorry, I get so excited. To do inference about the difference mu1 subtract mu2 between the two means, between the means of two populations, we start from the difference between the means of the two samples, which is x bar sub 1 subtract x bar sub 2. So note to self, if you have the ones in the front location, you have the twos in the second location, it should look the same in both of these, right? So don't suddenly flip it to x2 minus x1, right? Just because it's positive or something like that, right? Like, don't do that. You have to leave the ones in the first location, the twos in the second location. So we're looking at to do inference about the difference between the two means of the populations by looking at the difference between the means of the two samples, right? So it's really kind of doing the same thing twice and then mushing it together and comparing it a little. So it's just a little different than before, right? We've been doing it for one sample, one population. Now we're just going to incorporate looking at a different population here, right? So comparing two means. Researchers, so it's the green bar, so we're back to the clicker questions, right? Researchers compared the balance of a sample of elderly patients with that of a separate sample of younger patients. They exposed members of each age group to unpredictable noises and measured the amount of forward and backward sway. What feature of this study suggests that two sample inference for the means of the groups might be appropriate? So we've got choices like both groups were exposed to the same noise, the noise was unpredictable, both groups were of patients, or the good one, the two groups were sampled independently, right? So the rest of them don't really have anything to do with anything, right? So it is that we have two independent samples, right? Like that's the whole catch that we need. So as soon as I heard elderly patients versus younger patients, right? That's all we needed, right? Because those are two separate populations, probably much more younger people than elderly people, but not if they're patients. Maybe there's more elderly patients than younger patients, right? So definitely wouldn't be equal number of people, right, in those groups. So it isn't anything beyond that information that we needed to look at. And therefore, it isn't anything but choice D for us to look at, right? So researchers compared the balance of a sample of elderly patients with that of a sample of younger patients. They exposed members of each age group to unpredictable noises. I can't believe I'm reading this again, and measured the amount of forward and backward sway. In order for two sample inference for means of the groups to be appropriate, what else must be true, right? So we had those conditions, right? So these are questions that are getting toward that condition list that we had. And our choices here are the two samples are the same size. No, they can be any which size, right? On the last slide, that's why I was saying there's probably more of one group than the other anyway. What else must be true? That the data have outliers? No, we'd rather they don't have outliers, right? That the data for the groups have skewed distributions. Generally, if there's an outlier, there's a skewed distribution. I mean, generally, but not necessarily, I guess. But none of those are great choices, right? A, the data suggests that the populations are approximately normal. That's the one we're looking for, right? And so we often have to plot the data, stick it in a dot plot, stick it in a scatter plot, stick it in a leaf and stem plot, stem and leaf plot, right? A histogram. we have to visualize the data to answer, is it skewed? Is there an outlier? Because if it's not skewed and there's not an outlier, and it's not like some weird flat thing, right? If it looks approximately normal, we're good to go, right? So I guess there's ways it could be bimodal and it would be out, but right, we're looking for unimodal, symmetric, not skewed, no outliers. And we have to plot these things to like make that decision. So the data suggests that the populations are approximately normal is one of the conditions that we need in order for two sample inferences for the means of the groups to be appropriate. For observations, I don't think we got this one yet. See, that's what I mean. Like, let me click over because I think there's stuff missing from that slide that's given to us in the book, maybe. Let's see, conditions. They're asking us about the size, right? So here we have our two sample T procedures. I'm not even sure if I got the size statement here. Yeah, see, so that means we have to go straight to the book probably. Let's go back to the question though to see what we're looking at. So from observations from a population with moderate skewedness and no outliers, the sum of the two samples should be at least. So just judging from the last chapter, we did get a very clear number, right? I've got the book right in front of me, so I'll see if I can see the page in 21. But we did get an exact number, and that was for moderate skewedness. We had to have an N that was at least 15, right? And so I think that's what's related here. And the sum of these two numbers have to be 15. But let's see if I can find the page in the book, because it's questions like that are unsatisfying when they don't set you up with the info. I see one thing about numbers, but it comes later about skewedness. And I'm the one who laced this stuff in. So maybe we weren't even supposed to answer this question until the end, right? Let's see. I see a size thing on page. I lost it. Yeah, so I don't see anything here exactly. I saw one thing, but like I said, I kind of lost it. And it referred to each individual number being greater than 5. So it wasn't even part of what I was looking for. So I'm the one who laced these clicker questions in. It was at the very end of the clicker questions itself. So potentially this one shouldn't have even been here. But we'll see, right? But in chapter 20, I know for sure we got this guide, right? As a moderate skewedness, we needed at least n equal 15, right, to compensate. So here's another one where, again, I'm going to lean on the definition from the last chapter. For observations from a population with strong skewedness and no outliers, the sum of the two sample sizes should be at least. There's strong skewedness, but no outliers. So we need a large N, right? And large N is defined to be 40 or greater, right? So again, it's the 40. I wish I had the exact phrase where they tell us. Because in chapter 20, it's on page 470, right? So for chapter 20, it's page 470, but we're in 21. So, and it's not on just like a quick list I can grab. So let's see if we can answer these. True or false? Unlike the T procedures for means, the F test for standard deviations, no, this is on a part we skipped, so that doesn't need to be there either, right? And then this one, let's see. I could tell you just from the chapter we're in, it's the subtraction one, right? Like what else have we looked at? Not multiplication, division, or addition. We were defining things to be subtraction. So that's just looking at that. The setup is the same. It's still researchers comparing the elderly patients and the younger patients. They're exposing them to those unpredictable noises and measuring the amount of forward and backward sway. To compare the means, they should give a confidence interval for the difference between the elderly mean and the younger mean. And see how here the subscript is the word elderly and the subscript is the word younger. And they could have easily said the elderly patients are group 2 and the younger patients are group 1. And so this is mu2 minus mu1. But nonetheless, we're looking at the difference between, right? We're looking at the difference between these two groups, right? And that's literally the definition of the difference, right? So it isn't any of the other operations, right? See here, it gets a little hard to look at, but that's all right. It's just hard to look at, right? And we have null hypotheses. I can tell you right away, without reading a single word, the null hypothesis is an equal sign, period, right? Period. So it's not C or D. And the null hypothesis is about mu, not about X bar, right? X bar is interpreting mu. It's inferring mu. So without reading a single word of this question, the answer is A. It is the only one that has the null hypothesis written correctly, right? The rest of them are garbage, right? And so B is out, C is out, D is out. They haven't even written a proper null hypothesis, right? And so we're still dealing with these researchers and the elderly and the young. And the question is actually to compare the means. They should test the hypothesis that the hypotheses of the null hypotheses that mu of elderly is exactly the same as the mu of the younger. So the mean of both groups are the same, right? Versus the alternative hypothesis that here we're saying the elderly are going to hear less of that the elderly are going to hear less of the unpredictable noises, right? So that's kind of funny because they didn't really say that ever. And so you really are leaning into the fact that they wrote the null hypothesis correctly, right? Like that's a win right there. Okay, so I better check the clock because I can talk. All right, so 2 sample T procedures, right? So back to the swirly slides. So that means we're back to like the providing information slides, right? So 2 sample T procedures. To take variation into account, ooh, that means we're getting to standard deviation, right? So to take variation into account, we would like to standardize the difference, the observed difference between the first group and the second group, right? So X bar 1 minus X bar 2 by subtracting its mean, mu 1 subtract mu 2 and dividing the result by its standard deviation. This standard deviation of the difference in sample means is, so that's the standard deviation. If you look at it, it tracks, right? Like we've got, if you just look at one of them, right, you've got sigma squared divided by n, all square rooted. You can distribute the square root to the top and bottom, just of one of these terms though, right? Not of the addition, but we're just looking at like one of the terms. Then what we have is the square root of a square. So that just leaves sigma, and then divided by root n, sigma divided by root n, right? That's fine. That's something we've been looking at. That's been the standard deviation or standard error, depending on which chapter we were in. And now, right, we're talking about the difference between the difference of the means and the difference of the population means. So the numerator, or I don't refer to numerators yet, but the difference of the sample means subtract the difference of the population means, right? And then we're going to have this as a standard deviation. So because we don't know the population standard deviations, we estimate them by the sample standard deviations from our two samples. The result is the standard error. So when we use S, we get a standard error, not a standard deviation. The estimated standard deviation of the difference in sample means is this then. So it's again a bit of subscript. So you have the standard error of the difference of the sample means, right? Which equals, now we don't have sigmas, right? We're in a place where mu is unknown and sigma is unknown. And so we just use S's. And we do have all of this. If you remember the contingency table that we have N sub 1, S sub 1, X bar sub 1. Right, we're given that information. And so we have this info, we just have to stick it in here correctly. So S sub 1 squared, right? You have a superscript, which is a squaring function, and you have a subscript, which is just an identifier, right? So there's a lot of notation here. I agree, right? Hard to look at. But hopefully it's comfortable enough through the Z procedures and T procedures to lend itself to this next step. Of course, if you're just a formula driven person, print that formula sheet out, use it at every instance, and just practice the formulas all the time, right? So the two sample T procedures. When we standardize the estimate by subtracting its mean, mu1 and mu2, so mu2 from mu1, and dividing the results by its standard error, the result is the two sample T statistics. So get a load of this. That's why I was saying the difference of the sample means and the standard and the population means, right? So you have three differences up there, the difference of the differences, right? And then on the denominator, you've got that standard error that we just described in the last slide. So this is your T statistic. If you're asked for the T statistic, here it is, right? Note to self though, mu1 minus mu2 is always going to be 0, right? Because we are saying these two things are equal. That's what we go in believing, that there's no difference between the way old people hear and young people hear, or there's no difference between the amount of swaying that they do, right, when they hear these weird noises. So that's what we believe. So even though this is the visual, the second term on the numerator, it goes away just like in the last T procedure we were doing. The two sample T statistic has approximately a T distribution. It does not have exactly a T distribution, even if the populations are both exactly normal. In practice, however, the approximation is very accurate. There are two practical options for using the two sample t procedures. Option one, with software, use the statistic t with accurate critical values from the approximating t distribution. That's not what we do. Welcome to option two, right? This is UNM's option, right? So without software, use the statistic t with critical values from the t distribution with degrees of freedom equal to the smaller of the degrees of freedom. So you find the degrees of freedom for sample one, which is n sub 1 minus 1, and you find the degrees of freedom for sample 2, which is n sub 2 minus 1, right? And you say which is smaller, because the smaller one will represent both groups, right? If I have 35 dogs and 25 cats, right? Then both groups have 25 members. So I can use the lower number, right, of the two sizes and use that degrees of freedom, because the dogs have more individuals in the sample, right? And those individuals aren't also measurable in the smaller sample. And so what we do is we find the degrees of freedom for each group and we choose the smaller one, right? So the significance test gives a p-value equal to or greater than the true p-value. So we use option two. That's our option. Okay, so still on the info slide. Let's take a look at the confidence interval notation. So draw an SRS, a simple random sample of size n sub 1 from a large normal population with unknown mean mu sub 1, and draw an independent SRS, simple random sample of size n sub 2 from another large normal population with unknown mean mu2. A level C confidence interval for the difference between the population means, so mu1 take away mu2, is given by the difference of the sample means plus or minus t star times the standard error. So we're looking at, in the parentheses, right, x bar 1 minus x bar 2, that quantity plus or minus the critical t value for the confidence level that we're given, times this work of art, right? The square root of the quantity S1 squared divided by N1 plus S2 squared divided by N2. Here, T star is the critical value for confidence level C for the T distribution with degrees of freedom. For us, option 2, the smaller of n sub 1 minus 1 and n sub 2 minus 2. So pick the smaller of the degrees of freedom, as we were saying. Whew, that was quite the mouthful. Okay, so now we're to the tests, right? So the two sample T procedures hypothesis tests, right? To test the hypothesis of the null hypothesis, which states that mu1 is equal to mu2. So we go in believing there's no difference between these two populations, right? The mean for the cats is the mean for the dogs, right? The true population mean for the elderly is the true population mean for the young people, right? We go in believing this. We go in believing there's no difference. There's nothing to see here, right? Like, why are we even looking at this? That's what we go in believing. So mu1 equals mu2. Calculate the two sample t statistic as the one they just gave us. Note the minus mu1 minus mu2 bit is gone, because if you solve above for mu1 minus mu2, that is to subtract mu2 from both sides, you'll have one side equal to mu1 minus mu2, the other side equal to 0. So mu1 minus mu2 equals 0. And that second part of the numerator, the second term is gone, right? So the t statistic reduces to this, which is nice. I'm glad they wrote it, right? So it's actually just the difference between the sample means and then divided by the standard error here, right? Or the approximate standard deviation. And it's approximate, right? Because we're adding the two, what would be standard deviations together. It's really the two variations together and then rooting the sum of the variations, right? So find and almost the variations, because we're not using degrees of freedom on the bottom even, but still that's like just in like little bits of the conversation for those of you who got it. Otherwise, not that important. So find p-values from the t-distribution with degrees of freedom from either option 1, which we don't do, or option 2, the smaller of the degrees of freedom. So n1 minus 1 versus n2 minus 2, right? And here we have an example, not an example really. We're on the slides. Note the green solid line up there means we're on the clicker questions now. I kind of like the clicker questions. A dairy scientist, we talked about this a little, right? A dairy scientist compared milk production of cows fed 2 diets. He randomly divided a set of cows into 2 groups. One group was fed diet 1 for a month, the other was fed diet 2 for a month. Here are the milk production results. So when he randomly divides a set of 10 cows into 2 groups, they're saying that's 10 cows into each of the groups. So that's not how I was interpreting the question, but I'm glad they clarified it for us in this table, right? So my paper out, but I don't know if I need to. I don't. We're looking for a visual here. So we're looking for what is the standard error of the difference of the sample means, right? And we said that the standard error was the square root of S1 squared divide by n plus the S2 squared divide by its n, right? So if we look at our options, A doesn't have a root, B has a subtraction, and D has a subtraction. The only one it can possibly be is C, right? That's the only one. And it's just a matter of like visually matching up the pattern, right? Math, I've been told that by some people that it's like the study of patterns, right? So if you're good at pattern recognition, always have your formula sheet there. If you just look at the formula for standard error and then look at which one of these look like that, right? Then you're golden here, right? Like this was another question that we didn't even actually need to read. We just needed to know what the standard error looks like, know that it can't possibly be the ones with subtraction or the one without a square root, right? And then we're left with one possible correct answer. So try, right? Don't just randomly guess at these when you're stuck. Try to actually like dissect it, because usually there's only one. Well, of course, there's only one answer that's right, but sometimes you don't need the question to get yourself there, right? You just need the formula. So here we're with those cows again, and still with the same chart, I believe, at least the standard deviations are the same. Using option 2, which is our option, what would be the degrees of freedom, right? So n 1 minus 1 is 9, right? The sample size for the option 1 group is 9. And the sample size for the option 2 group, I don't like they would use the word option there because that kind of implies our thing, but diet 1 versus diet 2, right? So for diet 2, again, we're looking at 10 minus 1. So both of those groups have a degrees of freedom 9, which is the smaller of 9 and 9? Well, it's 9, right? So if they're the same, then it's just 9, right? Okay, same cows, same situation. They tell us our null hypothesis is mu1 equal to mu2, and they want to know what is the two sample t statistic for using this hypothesis. Again, option B is not correct. There's a subtraction in the square root term. D is not correct. There's a subtraction in the square root term. A is not correct. There's an addition in the difference of the sample means. The only one that can even possibly be correct that has a subtraction in the first set of parentheses, which the first parenthesis missing, but right, we have x bar 1 minus x bar 2, and then divide by the addition of the standard deviation or the variances before you take the square root, which gives us the standard error, right? So just looking at the form itself, not even verifying that they didn't switch the numbers up on us, just looking at the forms, that's the only one that goes minus sign, plus sign, the only one, right? So that's our option. That's the only one that can fit. Still with the cows here, right? What do we have this time around though? We get a little bit more. So the two sample t statistic, so the two sample t statistic, they calculated it for us, is negative 0.79, right? The t statistic is negative 0.79. If the test is one-sided, what is the p-value? So they gave us a little excerpt of the chart here. We said the degrees of freedom was 9. So we go to the 9 row, right? And we look at the absolute value, which is 0.79. And 0.79, let's see, let me bust out the annotator. It won't be smooth because I'm not on the tablet, but it'll still be all right, right? So our 1.79, okay, let me try that again because I didn't know what I was doing. For degrees of freedom 9, right, is going to be here, greater than the 0.7, but less than the 0.89. And so they tell us for a one-sided test, then what are our p-values between? They're between the 0.25 and the 0.20, but you have to reorder it so that your 2.0 is on the lower side and your 2.5 is on the higher side, right? So let me close that. And then the answer is in fact the 0.20 to 0.25. So we're using table C on this exam pretty heavily, right? Let me clear the annotator. Okay, so the confidence interval for mu1 minus mu2 is, we need a difference in the first, so not A, of the sample means, so not D. So that leaves us with B and C, plus or minus T star, check, check, times, in B, they put the T statistic there. We don't need that numerator stuff, X, the difference of the means. We need just the standard error, right? Because in the past, when this was chapter, whatever it was, chapter 16, confidence intervals, right? We would have a X bar or an X plus or minus, probably X bar, but X bar plus or minus Z star times the standard deviation, right? Then we beef that up to say X bar plus or minus T star times the standard error, right? Now we have the difference of our X bars plus or minus T star times the approximate standard deviation or the standard error, right? So it's choice C because it's the only one that matches. And literally, this is one where like you can just, I think that's for you, Eliza. Can you open the door, please? Thank you. That must mean it's 12. Okay, so again, just have your formula sheet out. You can pick this one right off of there, right? And we're back to the slides now. So we're going to get some examples that are like provided by the book now that aren't just the clicker questions, right? And they're all provided by the book, but whatever. So here's a quote unquote example, actually. So people gain weight when they take in more. Did you make me wait outside? Okay. People gain weight when they take in more energy from food than they expend. James Levine and his collaborators at the Mayo Clinic investigated the link between obesity and energy spent on daily activity with data from a study with N1 equal to N2 equal to 10 healthy volunteers, 10 who were lean, 10 who were mildly obese but still healthy. They wanted to address the question, do lean and obese people differ in the average time they spent standing and walking? Plan. Give a 90% confidence interval for mu1 minus mu2. The difference in the average daily minutes spent standing and walking between lean and mildly obese adults. Solve. Examination of the data reveals all conditions for inference can be at least reasonably assumed. The distributions are a bit irregular, but with only 10 observations, this is to be expected. But 10 plus 10, right, gives us 20, which is greater than that 15 that we were looking at earlier. So the solve part continued. The descriptive statistics are such that there are 10 lean people, right, with a mean of 525.751 and standard deviation 107.121. And we have a second group of obese individuals. I need a tissue, but I took it to my room. We have a second group of obese individuals where still there's 10 of them, right? They have a mean of 373.269 and a standard deviation of 67.498. Okay, that's better. For using option 2, which is our option, right, which is called the conservative degrees of freedom in absence of technology, then since the sample sizes are the same, the degrees of freedom are the same, which is 9, we choose the lowest, which is 9, and then we find the T star to be 1.833. I'm pretty sure they just gave us that, not that we found that anywhere. Okay, so back up a little. Yeah, I feel like we just like are lacking some info here, right? Like we didn't really have to find any of this. They just gave us all of this, right? So they're just leading us through an example, not telling us to answer a question, right? So, so here we have the confidence interval as filled out by just inserting the pieces given to you in the table into the right locations. So X bar 1 minus X bar 2 plus or minus the T star they gave us. And then you have to fill out correctly the square root of the quantity of our S1 squared divided by 10 plus our S2 squared divided by 10, right? Then you clean up the difference in the sample means to get 152.482. And then you clean up the margin of error to be 73.390. And then you subtract it once and add it once to get this range, right? So 152 take away 73 gives us the 79, and then 152 add on the 73 gets us up to that 225, right? So that's our confidence interval about the true mean difference, the true difference of the means of the population, right? So using software, blah, 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 they show us that our confidence interval is narrower because option 2 is more conservative, right? So we're not as brave as to go out as far as the calculator, right? So that's what they're showing us with that one. And then the fourth step, Poya's fourth step, right, is this conclusion. Well, I guess Poya's fourth step is to check it. The book's fourth step is to make a conclusion based on the real world problem that we're given, which we didn't really necessarily get all this info, like they just gave it to us. So whichever interval we report, we are at least 90% confident that the mean difference in average daily minutes spent standing and walking between lean and mildly obese adults lies in this interval. See, that's what I was saying. Like, I feel like I missed. I probably was getting confused because like my kids were here and meeting and stuff. Oh, there it is. Sorry, I got too click happy. Now I'm way back there. Oh my gosh. Okay, I'm gonna cheat and just go to the slides because that got crazy. Okay, yeah, my kids came and I got a little like confused because they couldn't really talk to them or anything. But basically, no. Basically, back here on the plan slide, they just threw me for a loop because I'm used to seeing like the problem given to us and then us make a statement and plan and all that kind of stuff. So it was a little strange, but back here, and it felt strange too because I cut the slides up so as to put those quicker questions in there, right? And so it wasn't just like them giving us formulas and then them giving us an example. It was them giving us formulas, us seeing if we understood, and then coming back to the example, which maybe I should have put those in the opposite order, right? But anyhow, they give us this, and then in the plan stage, they do in fact ask us for the 90% confidence interval, right? So that's where they got the T-star from then, is they went and looked at the degrees of freedom 9 row in table C, the 90% confidence interval column, and then they found the T-star. That's what I was saying, like generally we go looking for this info. They found the T-star to be the 1.833. The rest of it was given to us, but they did do a little work to get that 1.833 from table C. Then they fill out this form and then they're out. So that's what I was missing. I was missing, where did the 1.833 come from, right? And why? So Here we have another example. Let's look at the statement and the plan, right? And that way we maybe wrap our whole heads around it. Community service and attachment to friends. State the problem. Do college students who have volunteered for community service work differ from those who have not? A study obtained data from 57 students who had done service work and 17 who had not. So two sizes, two different populations. One of the response variables was a measure of attachment to friends. Here are the results. So for the 57 students that did community service, they had a mean of 105.32 and a standard deviation of 14.68 of attachment to their friends, right? And then, so whatever those numbers mean. And then our second group, which was the folks who didn't do community service, then they had a mean of 96.82 and a standard deviation of 14.26. The plan is that the investigator had no specific direction, so just a not equal to, right? No specific direction for the difference in mind before looking at the data. So the alternative is two-sided, right? So we're looking at a two-sided test here. We will test the following hypothesis, that the null hypothesis that mu1 equals mu2 against the alternative hypothesis that mu1 does not equal mu2, right? So we believe going in that the true population means are the same. There's no difference in community service and not community service. People are attached to their friends, period. That's why they're friends, right? Otherwise, the investigator thinks, I don't know, I think there is a difference, but I'm not sure which way, right? I'm not sure if the people who don't do community service are more attached to their friends because they don't have those like pseudo friends to helping people, right? So maybe actually those people are more attached to their friends. Or the other thought would be, well, people who do service for strangers probably super love their friends, right? Because if they love strangers, they're going to love their friends even more, right? So the investigator doesn't know which way it goes, doesn't know which one to assume it is. And so we're just looking at a two-sided that like, there's might be a difference, right? We just don't know which direction. Okay, so then the example continuing on, we solve by finding the two sample t-statistics. So what is the t-score here? It's the difference of the sample means divided by the approximate standard deviation or the standard error, right? So you just plug and chug the values from the last screen into the correct positions. And here they get a nice numerator, a nice denominator, and do the division there. I have a tendency to just stick the whole thing in the calculator or to work it piece by piece, kind of in reverse, doing the order of operations myself. Anyhow, they find a t-score to be 2.142. We don't care about the software. One of our degrees of freedom is 56, right? So we have 57 people, take away one gives us a degrees of freedom 56. The other group had 17 people, take away one gives us a degrees of freedom 16. And so we're going to use the degrees of freedom 16, right, for comparison. So what they do is they go to the table C, you go to the degrees of freedom 16 row, and you find the two t-scores that 2.142 is between. Then you follow those two columns to the bottom of table C until you're in the two-sided test row. And that is then the two p-values that they give, 0.05 and 0.04. To conclude, the data give moderately strong evidence. So our p-score is between these two values. So we're a little greater than the 0.04, but still less than the 0.05, right? And that means that students who have engaged in community service are on average, here they say more likely to attached to their friends, but they didn't say if there was a indication of which group it was. So I don't necessarily agree with this, right? They said we didn't know which group we thought was more or less, right? They said it was two-sided. And so I would have probably worded this differently, just to say that that the students who engage in community service on average do have a different level of attachment to their friends. We don't know if it's more or not. We're saying it's more because their number was more, but the investigator didn't say more or less, right? So we shouldn't go on to say more or less, right? We don't want to give the indication that we actually investigated that aspect of it, right? So because we didn't. So whatever, I'm arguing with the slides now, but so you can pretty much tell that's about the end. I didn't take out the slides for the tech stuff. And the last slide I want to go over here is robustness. So I'm going to read this one out real quick. The two sample T procedures are more robust than the one sample T methods, particularly when the distributions are not symmetric. When the two sizes of the two, oh, here's where we finally got one. When the two sizes of the two samples are equal and the two populations being compared have distributions with similar shapes, probability values from the t-table are quite accurate for a broad range of distributions when sample sizes are as small as n1 equal n2 equal 5. When the two population distributions have different shapes, larger samples are needed. As a guide to practice, adapt the guidelines for one sample T procedures to two sample T procedures by replacing sample size with the sum of sample sizes. Bam, that's the paragraph, little phrase that we needed earlier. We did this, we just didn't have permission, right? We used the chapter 20 stuff, and instead of a sample size, we use the sum of the sample sizes. So we did that, trying to suss out what the question was asking us, but here we finally have it in written form, which is satisfying. And then we have a caution in planning a two sample study, choose equal sample sizes whenever possible. The two sample T procedures are most robust against non-normality in this case, and the conservative option 2 probability values are most accurate because they're conservative, right? So boom, bam, that's the end of the chapter 21 information. It is tough. Feel free to reach out. I won't have office hours on Thursday or Friday. I won't be answering emails over the weekend, but when I do, I will be more than happy to help you. So you'll hear from me again on Monday, basically, or somewhere thereabouts. But as long as you're patient with me, I'll be patient with you, and I'm more than happy to extend things, explain things, go back over things once the break is over. So thank you very much. Have a great break. I will see you on Tuesday on campus in a week, right? Bye. Thank you, you too.